Good afternoon, everybody. I'm happy to welcome Dr. Luca Furieri as part of the AI and data talk series that we are organizing for the ACE network. And this actually, the talk of today given by Dr. Luca is about closing the loop between optimal nonlinear control and learning-based optimization. So Dr. Luca Furieri is an associate professor in the Department of Engineering Science at the University of Oxford, where he began in June 2025. His research focuses on optimal control and optimization for distributed decision-making and large-scale cyber-physical systems. He received the Swiss National Science Foundation Ambizioni Career Grant in 2022, the IEEE Transaction on Control of Network Systems Best Paper Award in 2022, and the American Control Conference Hugo Chuck Best Paper Award in 2018. So, well, we welcome actually Dr. Luca, and Dr. Luca, the floor is yours to start your presentation. Before that, I want to remind the audience that Dr. Luca is able to answer your questions at the end of the session, at the end of the talk. If you have questions actually on the two parts that he's going actually to contribute with actually in his talk, then please actually write your questions in the chat, and we will be able actually for Dr. Luca to take them actually and try to respond to them. Thank you. Please, Dr. Luca.
Thank you very much, Nabil, for the very kind introduction, and thanks everybody for attending. So today I would like to try to introduce you to some recent work that my colleagues and I have been doing at the intersection of optimal nonlinear control and learning-based optimization. Specifically, we have tried to embed neural network components within control loops and optimization algorithms, while trying to guarantee fundamental properties such as closed-loop stability for the case of control and convergence to optima in the case of optimization. The talk will be, as Nabil mentioned, divided into parts, and the first part will deal with the case of optimal nonlinear control, while the second part will deal with learning-based optimization. So the main motivation behind this emerging field is the success of neural network control in several real-world applications. In these videos, I'm showing some examples from robotics. In the first video, we can see how neural network policy is used for industrial manipulation, for grasping objects of different sizes in cluttered environments. In the second video, neural network policy has been trained for an aquatic robot to imitate the behavior of a real snake that swims in the water. And this robot is able to reproduce the behavior of chasing a prey, shown in green light, and also escaping predators, as shown by the red lights in the video. And the last example is drone racing. Neural network policies are even able to beat the human champions in drone racing. So it's pretty clear from all these examples that neural network controllers offer a very high degree of flexibility, and this is due to their ability to optimize for very complex objective functions that are usually beyond the ones we usually consider in control. So when it comes to neural network policy, to neural network control, I think there are two main challenges that we have to deal with. The first challenge is how can we certify closed-loop stability not only after training a policy, but during the learning itself, because usually we will be limited by time budgets, and we want to at least preserve stability, even if optimization is stopped early. Here, the goal is to then guarantee stability for all possible choices of the weights of these neural networks. And the second challenge is linked to how do we even navigate the highly complex and non-convex optimization landscapes that are inherent to these trainings of neural networks. So here the goal will be to converge, for algorithms to converge fast, and to good solutions in these non-convex landscapes. Now, what I will try to do today is to propose a unified methodology to mitigate both of these issues. And the punchline of this methodology is to try to shift our perspective from designing a neural network stabilizing controller to instead designing a neural network closed-loop map that is stable by design. And we will see how that can be done in practice. So part one will be about stable neural network closed-loop maps for nonlinear optimal control. And this is mainly the work of the paper that my colleagues and I have done in the papers listed here. So in our work, we considered a rather common scenario in engineering, where we have a frequent availability of stabilizing controllers for complex systems around equilibria or reference trajectories of interest. In the first video, I'm showing the case of a modular origami robot developed by Jamie in the group of Jamie Pike at EPFL, where essentially these triangular modules have been connected together to create this robot, and a distributed PID policy has been designed to guarantee a stable behavior around this trajectory the robot walks about. The second example is an all-terrain legged robot, which has been developed by the Oxford Robotic Institute to perform industrial inspection tasks, such as crossing these obstacles or walking upstairs in a stable way. Now, I would argue that, however, stability may not be enough. Indeed, let me mention that these videos have been sped up by several times because the behavior of the systems is stable but extremely slow. So there is a lot of performance that we can still squeeze out of this system. The question then becomes, how can we boost the performance of these systems without compromising the stability guarantees that have been designed for them? So we consider the problem of performance boosting, where we are given a nonlinear system that is either open loop stable or it has been pre-stabilized, as in the case of the applications shown in the previous slide. We want to design a performance boosting controller. That is, we want to solve a nonlinear optimal control problem, where the goal is to design a policy that optimizes some control cost for an infinite horizon on average over disturbances. There is a hard constraint in the problem, which is we want to get a policy that is guaranteeing closed loop stability. And the cost function can embed performance, such as task execution, safety, robustness, and so on. The goal is to leverage the flexibility of neural networks while harnessing the assumed open loop stability for control design. Let me introduce some quick setup. In this simplified setup, we will consider state feedback control. And we have a nonlinear system where W is process noise disturbing the trajectories, and the control policy is a dynamic policy that depends on the entire history of the states. We can describe this system in operator form. So essentially, we can stack together all the variables over an infinite time horizon and define signals in bold notation. Now, by defining these signals, we can rewrite the system in this operator form, where F is the open loop system and K is the controller. For example, just to have an intuition of what this means, if we consider an LTI system, the function f of xu will be simply an infinite dimensional matrix A times x plus b times u that connects the signals to their next iteration. We need also to define a notion of stability, and in this talk I will focus on L2 stability. This means that we consider a signal to be stable if it has a finite energy, meaning that the sum of the squares of its values is a number less than infinity. We say that an operator is stable if it maps a stable signal into another stable signal. So an operator essentially is stable if it doesn't blow up the energy of the signal that it has as an input. At this point, we are ready to define what we mean by stabilizing controller. A controller is stabilizing if the closed loop operators mapping the external disturbances to the trajectories of the states and the inputs are stable operators. So if we consider our control loop of our system F and our controller K, this means that when we have some external disturbances that are finite energy, these trajectories of the states and the inputs remain finite energy. They don't explode to infinity. And the assumption we are running on the system is that the open loop plant is a stable operator. So the state trajectory will be stable if the input trajectory and the external trajectories are stable. So our first result is a parametrization of all nonlinear stabilizing controllers in this setup. Here I'm showing the proposed architecture in a block scheme. On the right, you can see our plant f of xu, disturbed by some w. And on the left, you can see the proposed architecture. The architecture of the controller is made up of two modules. The first module is this f hat, which is an internal model or a nominal plant that we know. So we assume to have some knowledge about the plant, and we insert this knowledge into this module. This internal model is used to estimate the disturbance trajectories by comparing the measured state with the prediction of our internal model. Now, the most important block is the second module, which is what we call a performance boosting operator. So essentially, it is an operator that maps the reconstructed disturbances in the control input entering the system. So why do we choose this architecture? First, because we have a sufficiency result. The controller K, made up as in the picture above, stabilizes the real system F if the two following conditions hold. First, the performance boosting operator should be an L2 stable operator. And second, its gain should be upper bounded by a quantity that is inversely proportional to the mismatch operator, so how much we don't know about the system, and the gain of the open loop plant. So essentially, if we knew exactly the system we are trying to control, this gain here will be 0, and then their second constraint will not be applied. Most importantly, we also have a necessity result. So if you assume to know the real system, which means the mismatch is 0, then the operator M becomes the real closed loop map from disturbances to inputs. And therefore, any stable closed loop behavior can be obtained by appropriately selecting this M as an L2 operator. So if you give me any stabilizing controller K, we can choose an operator M in L2 that reproduces the same exact behavior. Thanks to this universality result, the next question becomes how do we learn an operator M that achieves a very good behavior for our system? So how do we embed a neural network stable operator in our architecture? We proposed one way to do this in our recent work, which is based on a magnitude and direction neural network factorization of stable operators. So here is our control policy, and in state space, it can be rewritten as on the right. There is first, as I mentioned, a reconstruction of the disturbances, which compares the measured state with the predicted state from the internal model. And then the performance boosting operator is decomposed as the product of two neural networks. We have a magnitude neural network parameterized by θ1, which has the goal of designing the magnitude of the input vector. And we also have a direction neural network, which chooses the direction we should step into with the input signal. So the most important part is the magnitude neural network, because it should be a stable operator. And we chose to design it as a stable linear recurrent unit recently proposed in the paper shown below. This is simply, essentially, a linear system with a neural network output. So we embed inside of our parameters a bunch of matrices and the weights of a neural network. We then construct a block diagonal matrix lambda, where the entries on the diagonal are complex numbers within the unit circle. And we then run a linear system, a stable linear system with dynamic matrix lambda, whose outputs y gets processed by a neural network. And the output of this neural network is our magnitude signal. Now, what's important is that this magnitude signal will converge to 0 by design, because the linear system generating the outputs is a stable linear system. The direction neural network will be a simple neural network which checks the states and decides the direction where we should step into. There is a tanh wrapping it outside so that the direction vector is always bounded between -1 and 1. Overall, we get a parametrization of an operator in L2 that is divided into a magnitude and into a direction. So upon using this parametrization, we are ready to train a controller. This can be done in many ways. The most simple way is to define a cost that is a function of the weights of our neural networks, which is computed by evaluating a finite horizon cost over a set of scenarios that are linked to different realizations of the disturbances. This is essentially a forward propagation step. The second step is to backpropagate through the parameters of our magnitude and direction factorization. This can be done with off-the-shelf tools like TensorFlow and PyTorch. And to be noted that closed-loop stability is guaranteed even if the optimization stops early. So whatever choice we do for the weights, using this parametrization, we always guarantee stability. Okay, before going to numerical examples, let me summarize the main insight. The closed-loop stability property that we encode is completely independent of the cost function. And this is because stability is linked to the policy parametrization and not to the cost we choose to optimize. So the lesson is that we should be free now to embrace very complex reward and cost functions from reinforcement learning and try to use these costs and training loops for control purposes. We considered a simple numerical example, which we call the corridor problem, where we essentially want to control 2 point masses, the orange robot and the blue robot. And the goal is to stabilize these robots around some target positions. So the orange robot should stabilize around this target in orange, and the blue robot on the target in blue. They should do so, however, while avoiding collisions between each other and also avoiding collisions with the obstacles shown in green. To do this, we can now run a separation of concerns. We first design a simple stabilizing base controller, which in this case is, for example, simply a linear spring that is at rest on the target. This base controller will be actually very bad because it will not avoid collisions, it will have a lot of overshoot, and so on. So then we run a performance boosting procedure by defining a cost function that is made up of several components. A cost that penalizes reaching the target, a cost that penalizes collisions, and a cost that penalizes collisions with the obstacles. And this can be done in many ways. For example, defining a collision avoidance loss that is very high when the distance between objects is very small. All right, so let's see what happens. We try to train these point masses over 500 different initial conditions. And indeed, the masses learn to alternate their passage through this narrow corridor while converging to the target positions. Now, the most important property is that closed-loop stability is guaranteed even if we stop the training early. So if we don't train the weights of the neural networks at all, you see that the robots are still stable around the target positions, but they collide and they have a very bad behavior. As we increase the training episodes, they learn to first alternate their passage and then to pass vertically through this narrow passage. But the closed-loop stability is embedded in the policy parametrization. Another example comes from safety concerns. So in learning-based control, a common way to embed hard safety constraints is to add a safety filter on top of the learned control input. And this is usually done using online optimization, checking if we need to tweak our learned input to make it safe. And this is usually very computationally expensive. So using a performance boosting procedure, we can try to significantly reduce the activations of safety filters by embedding soft safety specifications in the cost. What we tried was, inspired by the paper shown here, was to promote constraint fulfillment through barrier functions. But the key was also to promote invariance of the safe region. The safe region is usually defined through a barrier function h, and we penalize the the increase of this barrier function. So we encourage the system to remain safe even at the next time instant. Indeed, we considered again the corridor problem, but we added an unsafe region, essentially a wall we don't want to crash into. And without the invariance term, we have to activate a safety filter 43% of the run, because otherwise we will run into this wall. Instead, adding invariance penalization, we only have to activate a filter 1.4% of the times. And the last example I would like to highlight is the one of logical specifications. So we are not tied anymore to having costs that are composed of the sum of many stage costs, but we can also consider very sparse rewards that are coming from logical specifications. In this task, we want the blue robot to perform a waypoint visiting task. So we want it to first visit the point B, then point C and point A, and stabilize around A in the end, while the orange robot should do the opposite, circle A to B to C, and then stabilize to C. We see that our base controller is indeed able to stabilize the robots around the target positions. However, with performance boosting, using logical specifications proposed in this paper, we are also able to perform this logical task, so visiting the waypoints in the correct order and then stabilize around the target position. All right, so the main punchline was using neural networks to design stable closed-loop behaviors instead of directly designing a stabilizing policy. And in part 2 of the talk, we try to see if this shift in perspective can also be useful for numerical optimization. So let me proceed to the second part of the talk, where we essentially change topic, apparently. And the second part is about learning to optimize, which is the discipline of embedding neural network components within optimization algorithms. And the goal will be to hopefully outperform classical algorithms thanks to the neural network component. We will focus on convergence guarantees both in convex and non-convex landscapes. And this is the work with my colleagues, mainly in the papers listed here. So algorithm design. When we design an algorithm, we usually have in mind solving an optimization program of the form shown here. We want to find a vector of optimal decision variables that minimize a cost function f, subject to some constraints on the variable. It's very rare that we can solve these problems analytically. So usually we use an iterative optimization algorithm that starts from a candidate solution and through iterative updates, hopefully converges to a better solution. Now, when we design an algorithm, we have to satisfy at least the following 3 requirements. The first requirement is that the iterations should converge and should provide feasible iterates, so that we remain feasible and safe at all times. The second requirement is usually speed. We want to find at least a stationary point of this landscape in as least steps as possible, as few steps as possible. The third requirement is the quality of the solution. Especially in non-convex landscape, we might have stationary points with a very high cost. So we want to find the ones that have a low cost and hopefully the global optima. Now, algorithm design is a huge topic, and there have been mainly 2 philosophies behind algorithm design. The philosophy of analytical design is the one we are more familiar with in control and optimization. Essentially, we define a problem class mathematically, such as the class of convex problems, the class of linear programs, the class of Polyak-Losiachevich gradient dominated function, and so on. And we design an algorithm that comes with formal guarantees for this class. The algorithm we design will then be used to solve new instances of optimization problems coming from the class we have defined. The completely opposite way of thinking about this is coming from machine learning, where we don't usually have a mathematical description of the optimization problems we want to solve, but what we have is a deck, a set of example optimization problems we are interested in solving. The idea is then to consider tunable optimization algorithms that overfit their performance to these example problems. This is essentially a training procedure that gives us a learned algorithm. And this learned algorithm will be used in the future to solve new optimization problems that are not seen before, and hopefully the algorithm will still work well. So starting from the analytical design philosophy, there have been a lot of significant results coming from the control community, especially in interpreting classical optimization algorithms such as gradient descent, accelerated algorithms like Nesterov, and so on, as low-risk systems. So the insight is that we can see an optimization algorithm as a feedback loop between an uncertain plant, which is given by the gradient of a function, and the plant is uncertain because the algorithm doesn't know a priori the function it's going to optimize, with a linear controller with memory parameterized by matrices A, B, and C. For instance, the vanilla gradient descent can be rewritten as the choice of these matrices A, B, C, and D as essentially identity matrices. And the same can be said for accelerated algorithms. Now, the works by Lessard, Recht, and Packard, and Scherer and Ebenbauer also figured out that we can design new algorithms, so new matrices A, B, and C, by leveraging integral quadratic constraints and robust control theory. The main advantage is that by doing so, we can optimize the worst case convergence rates over classes of convex optimization programs. While the main limitation is that these procedures are limited to convex objective functions. Now let's review what the machine learning community has done for the problem. Well, the idea that has been proposed in these papers is to just let a neural network guide the algorithm updates. So a neural network is trained to check the current solution and output a new solution that hopefully is much closer to the optimal solution. This is usually done by training a set of parameters over an algorithmic performance metric. And the one that has been proposed in the literature is an empirical average over a set of example problems of a cost function that balances out a term that promotes convergence by penalizing the gradients, and a term that promotes the solution quality by promoting the cost itself. Now, it has been shown that this procedure is actually working very well in practice, and it also generalizes to very different optimization programs. However, there is absolutely no formal guarantee on what will happen as the iterations go to infinity when we let a neural network guide the updates. So today's focus will be to try to exploit the flexibility of learned updates while preserving the convergence and the feasibility guarantees that are essential in the optimization field. Okay, so I will now formulate the problem with some notation. We will consider calligraphic F to be a family of objective functions, for example, convex functions, smooth functions, PL functions, and so on. We will also consider a legacy algorithm pi, which is an algorithm that has already been developed to solve for objective functions coming from the class calligraphic F. Now we realize that some objective functions within a class are way more frequent than others. And I think a prime example of that is actually model predictive control. In MPC, we have to optimize over a set of inputs for a cost function that is essentially always the same, in this case, for a linear system that is always the same, and while complying with constraints that are always the same. And the main thing that changes from instance to instance is the initial state. Now, if we take all these input variables together into a decision variable xi, what we have to solve in a linear MPC is a quadratic program where the quadratic part is actually constant, and the linear part depends on the initial condition, and also the constraints will depend on the initial condition. So my message here is that, in general, we don't have to solve for all the quadratic programs, but some of these quadratic programs will be way more frequent than others. So we should consider function f that are drawn from a distribution of functions over a class. The goal is then to evolve the performance of a legacy algorithm pi over the instances taken from this distribution of functions. However, we also don't want to lose the worst case guarantees over the entire family of objective functions. We will consider two scenarios. Scenario A is the case of smooth and non-convex objective functions. Here, the legacy algorithm we want to evolve is a standard gradient descent, and the convergent guarantee we want to preserve is asymptotic convergence to a stationary point. So in scenario B, we consider a more complicated scenario where we have composite and convex landscapes. Here, we essentially want to minimize the sum of two convex functions. However, one is smooth and one is not smooth. And this can be used, for example, to model convex constraints. In this case, the legacy algorithm is usually more powerful than gradient descent, and the state-of-the-art is accelerated methods such as heavy ball, Nesterov, and other variants of these methods. Here, the convergence guarantee is not only asymptotic convergence, but actually exponential convergence, which is termed usually as linear convergence. So we want that the solution converges to a global optimum exponentially fast, at most with a polynomial term times a number between 0 and 1 to the power of the time. All right, so let's start from scenario A, where we want to learn to optimize for smooth but non-convex landscapes. The first main result is, if we want to call it like that, like a separation principle for algorithms. So if we consider iterations of the following form, where we first apply a step of gradient descent, which is our legacy algorithm, and then we add an evolution term, we have the following result. If the step size is small enough, and the sequence of evolution terms is a finite energy signal, then also the sequence of gradients will remain a finite energy signal. And in particular, this means that asymptotically, the gradients will converge to 0. The immediate implication is that we can then evolve gradient descent by designing a finite energy sequence V. In practice, this can be done by training an evolution term parametrized in the magnitude and direction form that we have seen in part 1. The second result is a universality result. So if we take any target algorithm that is known to converge to a stationary point for all the class of functions that are smooth, so give me any of these algorithms, then this target algorithm can be rewritten as a step in the gradient direction plus an evolution term that has finite energy. This means that we can learn over finite energy signals, essentially, to reproduce the behavior of any convergent algorithm in this setup. Now, the insight here is that, again, we should think about the problem from a closed-loop perspective. And in the proof, we construct a term V that reproduces the closed-loop map of the target algorithm sigma. And we then verify that such evolution sequence has a finite energy. To see how that works in practice, we considered an experiment of training a perceptron for image classification. This is the standard MNIST dataset, where we want to classify a dataset of handwritten digits to their label. This is done through a multi-layer perceptron with an H activation function. And now Xi0 is the set of initial weights of the neural network. The classifier prediction will define a cost function f of Xi0. So this is the optimization problem we want to solve. The first step is then to train this perceptron for a fixed value of the weights of the algorithm. So we take some, let's say, random values theta. We generate a sequence of evolution terms for this theta, and we see how well we can train the perceptron through the algorithm shown here. The second step is then to train the algorithm parameters themselves. So after training the classifier, we evaluate how well we could train it by checking how much time it took to get 0 gradient and to get a very good cost. We then backpropagate through the weights of these neural networks and update theta until we find a very well-performing algorithm. After training the weights of the algorithm, we compare with fine-tuned classical optimizers to see if you can outperform them. All right, so let's see the results. Here we see a comparison between the training curves of different algorithms. The one in purple is the algorithm we have learned, which is faster than classical algorithms that have been fine-tuned through gridding of the hyperparameters. This is kind of expected because we are essentially overfitting our algorithm to multi-layer perceptrons with tonnage activation functions. What is more interesting is that the same trained algorithm can still outperform classical algorithms for activation functions that have not been seen in the training set. So for a sigmoid function, we still outperform other algorithms, but this is still kind of expected because a sigmoid is very similar to a tonnage. It's more impressive that we can outperform classical algorithms for the case of a ReLU activation function. So this shows out-of-sample generalization capabilities of learning to optimize over convergent algorithms. Okay, let's now go to the second scenario of learning to evolve linearly convergent algorithms. Now, we have another result, which is about evolving a contraction. Now, the legacy algorithm will not be just gradient descent, but it will be any monotonically linearly convergent algorithm, which means that the sequence of distances to the fixed point or the global optima decreases monotonically exponentially fast. The result is that if the evolution sequence is designed to decrease polynomially exponentially fast, then the sequence of distances will remain exponentially convergent, however, with the same gamma, but with a different polynomial of degree +1 with respect to the one we started from. This means that we can evolve contracting algorithms by designing exponentially decaying evolution terms. The second result is about evolving non-monotonic accelerated algorithms, especially for the case of strongly convex optimization. The state of the art is using accelerated algorithms that, however, are not monotonically convergent. This means that they have a better convergence rate, but they converge through a polynomially exponentially decreasing function, which is not monotonic. Now, the result is a bit different now. If you give me an integer number n that is large enough for this quantity to be less than 1, and this quantity is made up of the polynomial r evaluated in n times the n power of the convergence factor, there will always exist an integer number satisfying this because the exponential factor dominates over the polynomial one. Okay, so give me this number n. If you apply a polynomially exponentially decreasing evolution sequence only once every n steps, so not at every step, the distance to the global optimum will still converge exponentially fast, however, with a degraded factor, which is not gamma anymore, but it's this product of these two numbers, and this factor is always greater than 1, so it will degrade the original exponential rate. This highlights a trade-off. There is a trade-off between how often we inject an evolution term and how much we degrade the convergence rate. Now, the proof idea is that the legacy algorithm will remain monotonic if we apply it n times without disturbances. So pi of pi of pi of pi will at some point become monotonic. And then we can fall back in the case of the previous slide. The last result is about universality. So if we take any linearly convergent algorithm sigma with rate gamma, this linearly convergent algorithm can be rewritten as the sum of a legacy algorithm pi and an evolution sequence, where the evolution sequence should decay exponentially fast, polynomially exponentially fast, and the legacy algorithm can be any legacy algorithm that is monotonic and Lipschitz with respect to its argument. Now, the Lipschitz assumption is not particularly problematic because many classical algorithms satisfy it. However, we need a legacy algorithm that is monotonic. The proof sketch is that we construct the sequence V achieving the same iterates as sigma. This is simply done by removing the effect of the legacy algorithm and adding the target algorithm. And then we subtract psi from both sides. This allows us to bound both terms in the following way. So the first term is bounded through the Lipschitz constant, where this part vanishes with gamma by assumption. The second part is nothing else but the term psi t plus 1 minus psi t, so the sequence of updates, and this also needs to vanish exponentially fast by assumption. So overall, the sequence that achieves the target behavior is also exponentially convergent. For this case, we considered the example of solving ill-conditioned systems of linear equations. So this is the very common problem of trying to find a vector psi such that A times psi equal B. However, we fix the matrix A and matrix B so that we induce a distribution over this class of problems, and we let delta A and delta B be some Gaussian perturbations to create different problem instances. Now, in general, we could invert or pseudo-invert these matrices, but as the dimensions increase and the condition number of this problem increases, this becomes computationally intractable. So what we can instead do is to formulate an optimization program, especially in this case a quadratic optimization program that minimizes the mismatch between AX and B. This mismatch should go to 0. This is a strongly convex and smooth program where the legacy algorithm can be taken to be the nested of accelerated gradient, which ensures linear convergence. For the test, we considered a very ill-conditioned instance of this problem, where the matrix A has a condition number of like 18 millions. This is because the entries on the diagonal are extremely large, of the order of 10 to the 8, while some off-diagonal entries are negative 10 to the 8. So the goal will be to learn an evolution sequence that learns and exploits this problem structure to improve over classical optimizers. Here are the results. We first try to solve the problem through standard gradient descent. And as you see, even after 10,000 iterations, the loss is still quite large. A much better performance is obtained by nested of accelerated gradient, which is a non-monotonically decreasing algorithm that can find a good solution after approximately 10,000 iterations. Instead, our trained algorithm can converge much faster to a good solution, and it does so by creating a behavior that cannot be reproduced by classical algorithms. If we zoom here at the beginning, our algorithm learns to initially follow the positive gradient, not the negative gradient, in order to accumulate momentum and have higher returns later. So this is an interesting behavior, and it learns to use the structure of the problem to solve it faster. So this brings me towards the end of the talk, and we have seen some topics at the end of non-convex optimization and nonlinear control theory. In the first part, we have used non-convex optimization and specifically neural network-based optimization to ensure stability for control systems. In the second part, we have done the opposite. We have used the nonlinear robust control theory to evolve classical algorithms with neural networks. The unified method we have proposed is to use neural networks to design closed-loop behaviors directly and not to design policies with the parameters of the neural network. Future work will focus on both the control and the optimization side of it. For the control side, it will be interesting to develop a new control-friendly reinforcement learning procedure where we learn over stable closed-loop maps and not over the policies. And I think it's also an important occasion to learn some lessons from AlphaZero as advocated by Berzekas, where we should probably not focus all of our effort into learning feedback policies, but we should combine a learned feedback policy with online optimization, for example, nonlinear model predictive control, to really achieve intelligent behavior of these systems. This is indeed what has been done for training AlphaZero in a sense. And another important topic is how to scale up these systems, not only in terms of having a lot of parameters, but in terms of scaling up to network systems where obtaining stability is much harder. Especially, it would be interesting to understand if we can get plug-and-play operation of neural network control policies. For the optimization side of things, the immediate first step will be to develop performance generalization guarantees to understand how well our trained algorithms will perform on new problems in a quantitative way. And there has been some encouraging work by the group of Bartolomeo Stellato on developing this kind of data-driven performance guarantees. I would also be happy to study the impact of learned optimization on optimal control, and especially model predictive control. So can we significantly evolve the performance of off-the-shelf optimizers such as iPopt or OSQP for model predictive control by overfitting to specific systems? And another important question is to understand more what is the link between control and optimization. To answer also questions of inverse design, such as let's take a nested of accelerated gradients, for which kind of control costs will it be optimal? And probably it will not only be optimal in terms of optimal worst case guarantees, but it will be optimal in terms of rejection to disturbances and so on. So with this, I thank you so much for your attention, and I'm open for your questions.
Okay, thank you, Luca, for your talk today. I think actually very explanatory. I wanted actually to invite the participants actually to write, if they have any question, to write on the chat their questions, and then actually Dr. Luca will be able to answer those. I had one question, but you mentioned it in the future work, is really actually about the RL. Why actually you did for the second part, actually you showed actually your algorithm for a classification problem, but I was wondering actually for a more complex problem, it is related to the deep reinforcement learning, for example, if your algorithm will be able to accelerate actually the convergence of the DRL in a problem related actually to robotics or any other problem. So, but you answered it's in your future work already.
No, that's a great question. I think it's basically an open question. One thing I can maybe add is that if we take the machine learning literature and learning to optimize, what they really focus on is the generalization guarantees. So, for example, they train this algorithm on MNIST, this is the dataset MNIST, and they show it still works well for classifying human faces. So that's one aspect that comes out of learning to optimize. In terms of control, I think what is emerging now is that we don't only analyze systems and interconnected systems, but we actually analyze dynamical systems interconnected with algorithms as a single closed loop system. I mean, the algorithm is a dynamical system itself. So understanding where this can play a role is very important. And I think convergence is the glue linking these topics together.
Right. Thank you. Any other question? Any question from the audience, please? You can actually type it in the chat. We'll be happy to take it. Okay, I'm not too sure. Can you type it actually on the chat, Dario, please? Or maybe you can go ahead.
Maybe
you can go ahead.
Maybe
Just go ahead.
if I just go ahead. Yeah. Yeah. Ciao, Luca. Very nice talk. Really exciting. Couple of questions on my end. One on the first, one on the second part. So on the first part, I was curious to know more in terms of how much do you need to know about the true dynamics, right? You have this kind of internal model control in some sense buried inside the neural network. And so I was curious about, how much do I really need to know about the true system? And for the second one, instead, I was curious about how computationally expensive is this sort of, meta learning in some sense, in the sense that, you're learning the algorithm that then learns the solution, right?
Yeah.
So curious to hear about those.
These are important aspects indeed. So for the case, for the question about the first part was, about the mismatch. How much mismatch can we tolerate? So the initial result we have is about a gain-based mismatch. Maybe I can move back to. So we are assuming that we know some initial estimate of the problem. Just a second here. Okay, and one can assume very simply that the real system is just the nominal 1 plus delta. Now, a few caveats. Yes, if we know a gain of this mismatch operator, then we can have this kind of bound based on the small gain theorem, essentially. However, a more fundamental question, which we haven't addressed, and I think it's important, is whether it's realistic that for nonlinear systems, the mismatch is a game-bounded operator. For linear systems, it's pretty straightforward. I mean, if we just consider, a linear system plus another linear system, it will have some kind of Lipschitz constant. For nonlinear systems, it's a bit more tricky. And I would say in many cases, the mismatch will not be game-bounded. So for that case, my answer would also be, it's probably better to see the problem from the input-output perspective and not from the state space perspective. Because if we have an input-output model, then it's more straightforward to define these gains. Instead, if we have a state space representation, it might be a bit more tricky to estimate, these gains in practice. Does it make sense?
Yeah, it makes sense. It makes sense. I was also curious if you tried an experiment, right, and see sort of what the performance was when, the true F was something, but then you ran the experiment with some kind of corrupted F, right?
We do have exactly this kind of robustness experiments for the case of point masses, the one I showed in the examples. And there, it's pretty straightforward to estimate an L2 gain of the mismatch from data, because it is, in the end, a linear system that we're trying to control. I think basically the question is about nonlinear systems, and that's a completely important topic that needs to be joined to this. Yeah. Regarding the second part, sorry, can you remind me the question?
Sure. Yeah, the second part was just about computational. How expensive is it to do this sort of learning on top of the learning, right?
Yeah. This is the bottleneck of meta learning. So you need to essentially run at a higher level of hierarchy optimization. One step of training your algorithm is solving an optimization problem. So it's very computationally expensive. The counterpart is that you have to do it only once. So the idea is we design an algorithm. This will take a lot of time, but this algorithm will be used in the future for many problems. And this is a fundamental problem of learning to optimize. And usually you try to do this training once offline.
That's clear. Do you have some kind of concrete numbers? I'm just curious to see, how hard is it, if I really want to try it out on some concrete problems.
Yeah, for the case of ill-conditioned linear systems of equations, it wasn't too bad. We considered, so for the structure of the algorithm, an LSTM architecture with a few layers, I think 2 or 3 layers really. And the parameters were around 10,000 in total. So that took on a standard computer like 1 hour of training kind of episodes. So why is it efficient in this case? Because we always have the same matrix A plus some perturbation, and backpropagating through the cost is not too hard. It's easy to compute these derivatives. If we consider like MNIST took a bit more time, it was still doable because we consider MNIST with very few layers, a very shallow neural network. For the cases we have found in the literature for more complicated problems, I think the training is more intense and it requires knowing how to train architectures in a standard way. It's not just, you throw a multi-layer perceptron at it and wait for it to train. This will break out very fast.
Okay, thank you.
Thank you, very clear. Thanks again.
Any other question, guys? If not, actually, the last question from my side, actually, did you try to compare, at least for the first part of your work, to the work made actually by Pete Zeller on actually on using IQCs actually to be able to guarantee the stability of a closed-loop control system with the neural networks? Did you actually? I'm sure you are familiar with the work actually there, because you have seen the papers of Lassar also there, and he's referred in there anyway. Had you had a chance actually to make some kind of comparison actually with that work?
I think the main thing is that this work is focusing on a problem that has already been solved using those things. So IQCs, for example, I'm not specifically familiar with the work by Peter Sayers, but the idea is to use dissipativity notions to design controllers that comply with certain kind of stability. And that solves also at the same time not only the problem of finding an optimal controller, but finding a stabilizing controller for a nonlinear system. The catch is that the parametrization of these controllers is not complete. So we can try to optimize a cost function and find the stabilizing controller, but we cannot explore all the possible nonlinear policies. Here, instead, we focus on another side of the problem, which is, let's assume we have already tried to control the system in a stable way, in a decent way. Then using this inherited stability, we try to explore a boosted behavior. So I think actually the two things are complementary, and we are relying on this literature to then run a new training that doesn't ruin the inherited property. IQCs are the way to ensure these properties in the first place. Yeah.
Okay, thank you very much actually for your time. So if there is no other questions, I thank you very much, Dr. Luca, actually, for accepting to come to give a talk today for our talk series. And thanks for the audience and for attending actually this event. Thank you. Bye-bye.
Thank you so much.
Bye all.
Thanks, everyone.
Thank you. Thanks.